my role today is to be the quantum engineer of the QEI co-founders team. I try to create bridges between the two worlds, which are on one way what you represent, most of you here, the academic world, and the other world, which is the industry world, where you have a lot of startups, large companies like IBM. We know this phenomenon with hype and stuff like that. And I try to understand how is this going on and how a better understanding of what the companies are doing can create opportunities for the QEI community as a whole. What I'm going to talk about today is first is trying to kind of reframe or redefine the notion of quantum advantage, energy advantage. It was initially designed by Alexia in a paper in 2001 in an archive. I try to refine this a little bit. The second is I'm going to look at some economic issues and concerns. How the economics of this potential market is going to affect what we do when looking at the energetics of quantum computers. The third one will be to look also as the most relevant applications, those that real users may use, and people like Joseph Miquel over there is going to talk about this on Thursday, and look at how it's going to frame the kinds of energetics issue we should look at. The fourth issue I'm going to talk about is look at new scalability challenges. Because when you look at new stuff like what Google did recently with the Willow chip, you see marvelous exponential corrections with error rates, but it uncovers new challenges that you have to look at, and those have a lot of energetic impact on research and academic research. And the last one will be to propose, during the flow of my presentation, new research avenues. And I don't mean to create research avenues for industry vendors, just that. I mean also to propose new research avenues for academic research. So creating again the bridge between those two worlds. So that's the map. I hope you like it, and you're going to see. And the main goal is not to provide answers, it's to ask questions. I'd say that's the basic of good research, is to ask the good questions and look at new questions that are being raised by the advances of science, the advances of technology, and so on. The first one was to reframe the notion of energetic advantage. It's easy to define that when you can make a comparison with an existing solution. So let's say you have a new VQE algorithm that does some chemical simulation, and you can compare it to an existing HPC solution. So then you're going to compare two solutions. You're going to compare the speed, the quality of the results, the price, and so on. And if there is an energetic difference in favor of the quantum solution, it's a clear quantum energetic advantage. That's simple. But the second case is, let's say you do something that's not classically possible for whatever reason. You have thousands of logical QEs. You simulate many quantum systems that have, I don't know, more than 200 orbitals, and it's not possible to do that with the DFT or FCI on a classical system. Then how would you explain what is the energetic advantage? And actually, you could define it very differently than an advantage. It's about the acceptability of the solution. And it's more an economical notion. It's boiled in the fact that you need to provide something that's acceptable from the business standpoint, or from the economical standpoint, or even from the societal standpoint. So for example, if you have a new systems or a new sets of systems that consumes more than a region in a country like France, maybe EDF is going to be in trouble to provide the energy to the guys running those data centers. So it's going to be a societal problem. If, on the other hand, the energetic cost is going to be acceptable because it's less than, let's say, the largest HPCs that you have right now, it's okay. So the acceptability is probably a better definition than just talk about an advantage, because you compare with something that doesn't exist. So that's the first point. The second is, let's look a little bit about some economics. So it's kind of a joke here, economics for physics, a physicist. On one hand, you have the benefits from a solution. So speed up. It can be the quality of the results you get for machine learning solutions, for example. It can be also the amount, the size of the required data that you need. Some quantum solutions are said to be less hungry for data, and that may be a benefit. And what's cost energetic is mostly the cost structure. So that's the economics. the cost side. And so if you do business, if you're a company, or even if you're a government or a public sector user, what you're going to look at is at the business benefit. And the business benefit is, what's the value of that? So the value is, let's say, more revenue, reduced cost if you're a company. In the private sector, it can be an improved service quality if you're a public services, for example. And it can be better competitiveness if you're a drug pharmaceutical company wants to design drugs faster than your competitor. So that's the business benefit. So in the end, the economical impact is called ROI. I don't know if you know that acronym. It means return on investment. And if I'm using a kind of a fake quantum physics parlance, it will be the scalar product of the practical benefit vector times the business benefit vector divided by the trace of the density matrix of the economics. It's just a joke for you guys. So it means that, and the problem is there noise over there. So maybe the density matrix of the economics is going to be problematic. You have obsolescence. So over time, your hardware loses value because you've got a new hardware coming up. You may have maintenance costs. You may have bad surprises, whatever. So you're going to have some noise over there if you want to put some more quantum physics. But there is another phenomenon where energetics will play a role, is at some point, those systems will get used by many people if you have some volume, and also if you have two phenomena which are economical in nature. One is versatility. It means that the solutions that quantum computers provide to organizations are as generic as possible. If I'm taking, for example, an NVIDIA GPU right now, you don't say NVIDIA GPUs are used only for one single category of machine learning solution. It's used for anything in machine learning, deep learning. It can be used also for Bitcoin mining. It can be used for scientific computing. Whatever you need, you can do it on NVIDIA, and they're worldwide leader right now. The second, which is sometimes connected to the other, is so-called platform effect. When you have a leading solution, software and hardware, you have a lot of people who develop solutions on them, and the value of the system is not just the raw value of the solution and the product, the hardware product that supports the software. It's the value of the whole ecosystem. Because you have choice. You can move from one application to the other on the same hardware. That's why your smartphone is on Android or iOS. It's a platform. And when that works well, it drives the economies of scale. And then you've got some back action because the economies of scale reduce the price and improve the business value. But the side effect of that, it's creating leaders, and sometimes it creates monopolies, like Microsoft and Windows, Android and iOS on the smartphones, and NVIDIA right now on GPUs. That's a side effect of that phenomenon. And you can wonder what's going to happen in the quantum computing world. We don't know yet. Is it going to be IBM leading that world? Are we going to have maybe two leaders for each qubit modality? We don't know yet. But these are economical phenomena to understand, because it may have an effect on the energetics of the solutions. Now, I'm going to reuse something we built about 2.5 years ago. It's the full stack of a quantum computer, starting with the application on the top and the lower layers, particularly the qubits over there, the device controls, so electronics, lasers, and then the enabling tech like cryogenics and so on. If you want to have a good view of the energetics of a quantum computer, you need to look at all these elements, and you need to connect them together. And I would say there are two kinds of approach there. One approach is a bit like what we do in quantum thermodynamics. We look at the qubits there, and then we move out in the stack, and you build the system. And the other one, and I don't think one is better than the other, they are just complementary. One way would be to start looking at the applications on the top, what are their requirements, and go down in the layers and match the system. So a kind of bottom-up approach, crossing a top-bottom approach, and to look at this. And if I was expanding this thing, use this nice animation, I learned that with my kids, so how you can program your PowerPoint. You can have two dimensions. So one is the one I described, and the other one is what are you doing there between fundamental research, applied research, experimental development, when you test some things in labs, and some products in labs, and the technology development, which is more industry-oriented. Let's say you want to manufacture chips on a wide scale with high-quality manufacturing processes, like at ST Microelectronics right now for Kobli in Grenoble. And a good project, I would say, as part of the QEI, would be a project that has those two dimensions. So crossing about 2 or 3 layers over there, and moving between fundamental research down to technology development at some point. Not necessarily at the beginning, but at some point. And one very good project, and I think it's one of the few in the world, that was created nearly 3 years ago, OECQ, which is run by Joseph Miquel over there, and the whole team is in the room, is a good example because it's crossing all the layers and all the columns merely. So that's a good kind of project that fuels the QEI and fuels the spirit of the QEI, making people work together. So I'm going to go through all the layers, if I have time. So the first 2 layers are going to be applications and algorithm. And it's going to be a mix of science and economics there. If you want to have a kind of very broad view of what people may do in the future with a quantum computer, I use this segmentation in 3 columns. One is people who do pure science, fundamental science. There's no business behind that. You don't win money. You do pure science. And the best example is people at CERN in Geneva. I'm going to be there in 2 weeks, by the way, for a conference. But they do high-energy particle physics. They do segment the stuff that comes out of Atlas experiment to look at the boson Higgs. There's no business there. The business is in the magnets that powers the system, the LHC. But it's very interesting. That's fundamental science. The same for people who are looking for dark matter over there. And then you've got a lot of condensed matter physics and pure physics developments, which are done, and which may use quantum physics simulation using a quantum computer. And that's where it starts. Right now, there are a lot of people doing very interesting things there. The second one, which I believe, and I will explain why, is the sweet spot of the market, is going to be applied research for a mix of academic and industry organizations who want to develop new products, usually based on digital twins, which can be a molecular digital twin, which can be a material digital twin, which sometimes can be a more complicated system digital twin, like when you want to design and optimize a semiconductor. Sometimes it can be linked to climate, not solve the climate change, but at least modelize the climate. And all of this is about using a quantum computer to design something new, which then is manufactured classically. But it's still research. It's fundamental, it's really research. It's complicated, and it's using a particular kind of algorithm. It's mostly about materials and chemical simulations. And I will explain why it's important. The last one, which is troublesome to some extent, is what I mentioned as kind of business operations. It's optimizing the distribution of energy. It can be about optimizing transportation, logistics, retail, telecommunication, financial portfolios in banks. This is day-to-day businesses. This is when companies need to use the systems each and every day. The problem is those systems, to be workable using a quantum computer, they're going to use different kinds of algorithms. Most of them won't use the chemical simulation stuff you have here. They're going to use optimization algorithms or machine learning tools. They won't use chemical simulation. They don't care. So you don't optimize a financial portfolio or optimize the locations of the base stations for telecoms with chemical simulations. And it happens that it's more difficult to develop algorithms there than here. So it may mean that this is going to be a significant market. This is a bigger one, but with less interesting algorithms at this point of knowledge. And so that motivates me and maybe you to look at this category of solutions in the context of the QEI. So now, what's the problem we're trying to fix? Let's come back, and there was a slide on that, I think, yesterday morning. This is the most detailed inventory of where the ICT, so information and communication technology, electricity is consumed. The whole stuff you have here, I will erase it, it's devices. So it's your TV, your smartphone, your PC. I don't care. Then you have about 40% here, which is all the servers around. Half of them, and it's very surprising, are in the telecom companies. Moving the bits is more expensive than computing and storage. It's amazing. And there you have all the cloud, all the servers, the Googles, the Microsoft, the Amazons, they're over there. And interestingly, you can look at this in terawatt-hour, which is an amazing number. But the other number that's important is in power, in gigawatts. So the total server market 2 years ago, it probably grew since then because of LLMs and ChatGPT and so on. It's only 52 gigawatts. It's not that much. It's about 40 nuclear power plants in France, more or less. 40, more or less. And the whole HPC is over there. So high performance computing, supercomputers, it's only 0.4% of the total and 1% of all the servers. And one big question I have here is, are we going to use quantum computing systems to reduce or increase that small share of the total using the chemical simulation from the second column of my previous slide? Or are we going to touch the whole thing here and grow or change the landscape of business applications? This is a question. I don't have the answer. I've got a hint because I think it's going to be difficult to reach that market, but it's a big question because the stuff we do to optimize the energetics of quantum computing may have more importance if it's going there than there. If it's just limited to a small part of HPC, maybe it's not a big deal. So that's an overarching question from the pure economical standpoint. So now let's move to algorithms. What is a good algorithm? It's a big question. I use this chart. I love this chart. By the way, Pierre-Emmanuel Meriot, one of the co-authors, is in the room. And it's a chart that's not related to my talk, but it's showing the three things you need to do nice stuff with the quantum algorithm. So you need superposition, of course. It's over there, coherence. You need entanglement, of course, and maximum entangled state, preferably. And you need the so-called magic, which is linked to the T-gates that are necessary to drive at least potentially an exponential speedup with your algorithm. Without the T-gate or Toffoli gate, you can't have that. So that's called magic. And you've got a complicated error correction system to put in place to do that. But on a practical basis, what do you need? The first one is what I described before. You need usefulness. The algorithm must be useful for something that makes sense from an organization standpoint. So forget cross-entropy benchmark and boson sampling from Google and others. It's useless. You don't have input data. You need to have input data, output data. The second is you need a speed up, but not necessarily a theoretical speed up. You need a practical speed up for a real use case in reasonable times. And you're going to see that's more important than having either a quadratic or polynomial speed up or an exponential speed up. The third one is quality. Do you have good quality results? And the quality can be measured in mostly two possibilities. One is better accuracy, typically for chemical simulations, or better heuristics when you use a combinatorial optimization when you don't have a perfect solution, but you need to have at least a good solution. And the last one is the data. A good quantum computing solution shouldn't use too much data because quantum computers are slow. The gates are slow, like Misha Woods explained yesterday afternoon. They are slow, so the good algorithm should have not much data in, not much data out, so not too many samplings, and avoid using, preferably, a so-called classical oracle, like the ones you use with the Simon, Bernstein-Vazirani, and Grover algorithms. So that's constraints. You need to know about these ones. So now I've got this map, which is very good. Can you read the names here? No, so it's all the known algorithms mapped with their connections. And there are big chunks here of algorithms. The first chunk over there on the top is the QUBO reformulations. So that's the stuff you do on D-Wave or Pascal in analog mode. The second chunk is all that is around VQE. And I think that Sabrina Maniscalco tomorrow morning and Arshit Verma from Evidan is going to talk about that on Friday. So one tomorrow and one Friday. So this is one big thing here. And the last and largest chunk is the middle, where everything that's related to QPE, so quantum phase estimate. So there's many algorithms which depend on the QPE, and this is the one I'm going to focus on. So now if you look at the speedups, the theoretical speedups you could obtain with a quantum system are either unknown, which is the case with most NISQ and variational algorithms, then polynomial, including quadratic, that's the one we have with Grover, and then superpolynomial, including weakly superpolynomial and exponential. So when you look at this, and you know about the asymptotic speedups, you know that you preferably should be here. Because the theoretical exponential speedup makes sense, and we'll see why in details. Then I map all the algorithms I know of, because there are many more than here. So simulation algorithms, so VQE for NISC, then QPE for FTQC, then search and combinatorial optimization here, then machine learning, there's a lot of stuff over there, then others, and the speedups. And I'm going to focus your attention on a couple of things here. One is everything that's here that's linked to analog models. I would say that D-Wave and the system from Pascal are probably underrated. There's not a lot of research there. There's not much research also on the energetic of those systems, which is quite good. But we don't know well, from a theoretical standpoint, which are the limits of those systems. And there are some. But there's not much academic work on that. So where can they go? How far can they go, particularly for running optimization algorithms? The second is all the bunch here, and we'll look at QPE later. And the third one is the famous Grover search. I mean, when you teach quantum computing, you always have these Grover explanations and how you program Grover thing. Usually, you don't care about the oracle. The oracle is a black box. You don't know what's in the box. And I'm going to focus on this one and then that one. If you look at the theoretical advantage of a quantum computer, most of the time you say, oh, we have this bad exponential curve for complicated problems, so-called untractable problem here in red. And you're going to have, thanks to the magic of a quantum computer, a better curve, the green one. And so you expect that at some point you're going to win all of that. The reality is a bit different, particularly if you take Grover. If you take Grover and you use a different scale, so instead of having a linear computing time scale, you use a log computing time scale. And based on a paper from Xavier Vintal, who's over there at CEI-RIG, and Edwin Miles Studenmeyer, who's at the Flatiron Institute in New York. I met him 3 months ago in New York. What they found out is even when using a classical computer that's based on a workstation with, I forgot, 4 CPUs from Intel, whatever the solution, they could exceed the performance of a Grover algorithms, including one that's implemented with a fault tolerance, until the classical computing time was exceeding more than 1,000 years. So that shows the big difference between a potential theoretical speedup and the real one you have in real life. So if the speedup is only asymptotic and it happens only after a couple of 100 years or 1,000 years, it doesn't make any sense to use it, at least if this is a generic proof, which I'm not sure of. They took a kind of generic way to implement that classically, based on the fact that the oracle can be executed fewer times in the classical emulation using tensor networks than on the quantum version where you need a square n number of circuit runs for your Grover. I tried to find out whether that was true for a real application, because this is theoretical. So I looked at a benchmark that was done by a German team with people from Bosch in Germany, and they did a kind of similar estimation, and they were trying to do some kind of job scheduling optimization. So let's say it's manufacturing optimization, moving the pieces in factories. And what they found out is about the same, but with a slight difference from the previous paper. What they found out was that with perfect qubits, they would quickly use Grover and beat the classical solution. But when you embed all the fault tolerance and all the quantum error correction, bing, again, you need to have several centuries of classical computing to be better. So the big question here is, why is that? And can we change that? So I would say that if you look at the sentence over there, it shows that if you have faster readout, maybe you can change the picture. So the readout question we had yesterday, the discussion we have with Misha and Wood, is very important. If you can speed up the readout, maybe you can change that picture. But speeding the readout is a thermodynamic problem. So it's up to you guys to work on that. And another interesting thing is you could be better with only 300 logical qubits, which is not so much. So that's a good news. It's potentially good news. Even though there's a problem in the previous paper, maybe there's a solution to make that possible. But the worst case scenario is having an oracle accessing classical data. That we don't know how to do that. It should use a quantum RAM, which doesn't exist yet. But there are still solutions around which can be studied. Now, if you generalize the question around optimization algorithms, it's a very complicated story. And I thank Adrien, because Adrien Sueur was there. I had a lot of discussion with him a month ago. If you look at the way we solve combinatorial problems, you have two main options. One is to find an exact method, and it's very costly. It's, for large problems, it can be intractable. And there are existing solutions in classical systems, particularly IBM Cplex, which, by the way, comes from France, from ELOG, based around Paris, and nobody knows now because they were acquired by IBM back in 2008. And you got a bunch of systems here. The most famous are Gurobi, Tabu Search, which are more or less focused on the exact method or approximate method. So this is the legacy, I would say. Those are the problem formulation. These are the existing classical systems. And now, where are the quantum solutions? And the colors are easy to understand. Orange is bad news, I would say. Yellow is maybe, maybe. Green is maybe, maybe yes. And it's very difficult to find a quantum solution that really brings value to find exact solution. There's no theoretical proof that you can have an exponential speedup over there. So it's very questionable, even though there are some FTQC, QPE-based algorithms that may land in that place. And then you have those analog systems which are mentioned just before. So these are the questions. And the questions I have are manifold. I mean, could we build Oracle-based algorithms with a real practical speedup, which is not obvious at all? Is there a way to find an exponential speedup, a practical exponential speedup with those combinatorial problems? It's not obvious. And the last one is how about the large-scale analog system that I already mentioned? Now, I'm moving to a different gear. DARPA launched an initiative a year ago called the Quantum Benchmark Initiative. I wonder what they got this name, by the way. It's similar to QEI. The benchmark initiative is about benchmarking algorithms, but mostly it was about estimating the resources for useful algorithms. So it was not about benchmarking a VQE algorithm running an existing IBM system. It was about looking at the real solution that brings value to organizations, not just for the army, I mean for large organizations, and look at the resources that were needed. And they found out that most of the algorithms that were bringing some value, they were requiring a lot of resources. So you have, for example, you may not know that amyloid beta binding, nobody knows what that is. It's about solving, understanding Alzheimer. So that's very valuable. Incompressible CFD, so computational fluid dynamics, it's very important for aerospace, for example. Corrosion-resistant material, it's easy to understand, maybe for a nuclear reactor. And you have also finding a new catalyst for nitrogen fixation, which is one of the most famous use cases that we know about producing ammonia more efficiently than what we do currently with the Haber-Bosch process. When you look at the resources here, it's just logical resources. I don't care about physics, qubit, it's just logical resources. You need a lot of gates, I mean, between 10 power 10 to 10 power 20, roughly. These are the number of gates, which turns into the fidelities you need for your logical qubit. But when you go in the rest of my chart, you need thousands of logical qubits, thousands, with those fidelities. So it's a huge challenge to build those systems which bring value. And if you look at the roadmaps of most of the vendors right now, it's over there for the next 9 years. Big question. So when are those guys going to be here? That's a big question. And should we focus as a community on that range or this range? It's another question. So if I look at then you see all of that is based on QPE, mostly, even Shor. So if I'm taking the ecosystem of the QPE, which is, I would say, one of the cornerstone algorithms like Grover in the quantum computing world, the QPE is the basis for nearly everything. You find it in, of course, in Shor. I put it in red because I'm wondering about the business value of breaking the internet. If you want to go in prison, whatever, maybe it's useful. But all the stuff here is based on QPE, particularly quantum chemistry, which I like most. Because, I mean, quantum chemistry, it's nice. I mean, you solve problems, healthcare, energy. Quantum Monte Carlo, it's for improving the financial portfolio, return on investment. It's less fun. I mean, people like it. Some people like it. It's less fun. So I'm going to focus on it. But you also have QSVT, which is a different algorithm, which is, by the way, used in here and there, and so on. And so I will dig into the resource constraints that are behind that. Maybe, yes. Usually people look at QFT, like Yasser Omar this morning. So we look at the resources of QFT. But I would argue that QFT is not interesting. It's a bit blunt, said like this. Why is that? It's because the QFT is a very small part of QPE, and it's also a very small part of Shore. If you look at the resource estimates for Shore, the QFT is less than 1% of Shore in number of gates, T-gates, whatever the way you account for it. So taking the famous Guinea-Cara paper from 5-6 years ago. Then if you look at Shore, Shore is a bit more complicated. You have the period finding part in that algorithm, so many T-gates, all the unitaries over there. But the luck you have with Shore is there's no encoding of the qubits at the beginning. So there's no input data here. All the data is encoded in the modular exponentiation that you've got here. That's this function. That's costly in Shore. And then the post-processing is not very complicated. And you can get rid of the QFT with a semi-classical QFT if you want. But then if you look at the QPE, and that's where the interesting part is starting for you guys, for the energetic estimates. If you look at the QPE has all the fuss, all the complexity. Because the QPE, it starts with the classical pre-processing based on R3 fork, FCI, DFT. There are many ways to prepare your simulation. And this simulation is used to prepare a state vector encoding that must be as close as possible to the target, the ground state that you want to reach. Then you have to prepare the unitaries, which are over there. So you've got n exponentiation of the unitary here. It's complicated. You need to be as close as possible to your Hamiltonian. And you've got many, many ways to encode that. And some of them are very costly. And the cost is over there. So you've got the order of magnitude, n3, n times 3, n times 5, n times 3 up to 2 power n being the number of orbitals in your molecular system. Then you have a repetition of that. It's very costly because it's increasing exponentially with the molecular size. So you've got many more shots as the molecular system is growing. And then you've got some post-processing, but which is not very costly. So the big question I have here is, can we estimate the classical and computing cost altogether when the system is growing? And is it going to be putting some energetic constraints both on the classical side and the quantum computing side? And I view that, I don't think it was the original view that we had with the QEI. I mean, the cost of quantum computing is going to be classical on top of the control of the qubits. There's going to be a lot of classical control, classical computing. If you don't account for this for any comparisons, it doesn't make any sense. And another issue is going to show up. Computing time. This is a kind of compilation of benchmarks done by GQI, an analyst company based in the US. And those guys, they plot a couple key algorithms, and they have these kind of potatoes over there. The potatoes are the same algorithm, but with different estimates. Gate times, qubit fidelities, and so on. So the worst are on the right. Usually that's the ions which are slow, and the superconducting qubits are more on the left because they are faster. But then the qubit fidelities may change that. The connectivity between the qubits may change that. But all in all, the bad news is at some point, the useful applications will bring a new problem, which is computing time. Not just the power and the energy, computing time. How does it turn out in the power and energy problem? It turns out that you have an energy that's very high to compute your system and a long time. So what can you do? The first thing you can do is you can reduce the size of your circuit. So there are many ways to do that. You have the code itself, you have the compiling, you've got the error correction, processing, pre-processing, post-processing. There's a lot of things to be optimized. It's mostly a software problem. It's energy software. Then you've got faster computing, which is more a physical problem. How can you have faster gates, faster readout, faster error correction? So that's a way to reduce the time, not the energy, the time. That's the hour of the watt hour. And then the last one is, how could you increase the power to reduce time? It's very simple. If you have a set of energy to spend, if you want to be faster, you have to have more power. Very simple. And so let's say you have 1 gigawatt hour. if you want to do that quickly, maybe you can parallelize the circuit shorts on many, many machines, and then your computing time is going to be slower. It's going to be faster. So there are a lot of trade-offs over there. So I invented my own acronym, so EFP, efficient, faster, parallel. And if you look at the kinds of disciplines which are embedded there, software on the top, hardware on the left, economics on the right, mostly. It's kind of wishy-washy, but it gives you an idea of the interdisciplinary way to look at these problems. And I'm going to cover in the rest of my presentation the things in green, which are lower in the stacks. This one is just below. This one is again below, and this one is going to be later. So let's look at compilers. We don't talk much about compilers when you look at the energetics of systems. When you do compile a classical program, you use the so-called von Neumann model. You have a code, you compile the code, and the code is executed on whatever data you use. So your email software on your laptop is one code, and the emails get in, gets out, it's storage. You don't recompile the code every time you get an email. Okay, it's simple. But if you look at quantum computing, it's a bit more complicated. Most of the data is in your code. The way you use it. If you encode it in an Hamiltonian, in an amplitude encoding at the beginning, if you use an oracle, the data is in the code. And the reason is in the table I've got there. The reason is we are using in-memory processing, which we don't use in most of the cases. Maybe neuromorphic systems are a bit different, but in most of the cases, you use in-memory processing. So the classical compilation cost is a variable cost against the data. So it creates some problem for the guys who want to optimize energy distribution. They want to do one quantum computing every minute in optimizing whatever business they want to do, let's say retail or public transportation, automatic cars, and so on. If you recompile a fault-tolerant code with thousands of logical qubits, which itself is an NP-hard problem, that's going to be interesting to look at from the time cost and the energetic cost. Because it's going to be repeated again and again and again each time you change your data. But then you can optimize the stuff. You can have libraries, you can pre-compile some stuff. Maybe you can optimize the whole organization. That's a software engineering problem. Now let's move down. It's going to be quicker. Error correction. Have you heard about Willow? Maybe? No? So Willow, the last 105 qubits from Google, archive in August, and Nature in, when was that? November. Big fuss and big communication with Google. And so they were able to create a logical qubit beyond the break-even, so better than physical qubits underneath. And if you want to look forward, is what are you going to do to do useful computing with that? If you want to do just a 10 minus 6 error rate logical qubit, which is on the left of my chart, you remember the DARPA chart, it's on the left. You would need 1,500 physical qubits. If you want to build a 10 minus 10, it's about 4,000, I think 3,700 physical qubits, based on their existing fidelities, which they want to improve, okay. But if you say you're going to need thousands or even hundreds of logical qubits, is it going to fit on one chip? The response is no. The plans, which are very aggressive from Google, are to squeeze 10K superconducting transport qubits on one chip, 10 centimeters times 10 centimeters. Colab, which was created by John Martinez, they want to do the same, 14 times 14, 20K. But if you take that math, you put only 7 qubits. And if you have even larger, larger surface codes, problems. And so many questions over there. And there's one I want to raise for you, is the cost of machine learning over there. Because a lot of error correction stuff is relying on machine learning. And there was a very interesting paper, this one here, published, I don't know, this summer, November, it's more recent, by Google, again Google. And by the way, there's a Nobel Prize over there, Demis Hassabis, the founder of DeepMind, who got the Nobel Prize in chemistry. And those guys, they designed a deep learning solution called Alpha Qubit, which improves the efficiency of the error syndrome decoding for error correction. but it doesn't scale beyond surface code distance 11 because they don't have enough training data beyond surface code distance 11. So my point here is the machine learning tools, which are used in many places in quantum computing, including error correction or even error mitigation, they're going to be costly. And it's going to bring some new classical costs to drive the systems. And this is something that should be investigated from the resource estimate standpoint, both logically and energetically. And so if you have this problem, what are you going to do? You're going to interconnect QPUs. And there you have a big open box of things to address, which is interconnect. And if you look at the various qubit modalities that you have around here, transmons from IBM, the cat qubits from Alice and Bob, again transmons from Google and Colab, and blah, 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 and all the ions, atoms, and photons, all of them, at some point, they will need to interconnect monolithic QPUs at some point. And this is going to be a problem because there are many solutions to do that. The best is when you use the same modality to interconnect than the modality of your qubit, typically photons. With photons, you use photonic for coupling. So it's cool, photons and photons. If you use trapped ions, it's not too complicated because you interact with the ions with the optical photons most of the time. So you are in a, I would say, an homogeneous system, not too heterogeneous. The problem starts to show up here in the superconducting world because you need transduction and photonic interconnect, which is very complicated. Thus the red here, if you use only microwave, short-range or mid-range microwave coupling, it's a bit easier. So thus the range I have here, blue is the chip, and from green to red is the kind of weight of the complexity of the interconnect. But that brings new challenges, again, from the energetic standpoint, because it brings challenges for the compilers, it brings challenges to the connectivity itself. So what's going to be the energetic cost of all the systems that connect the system together? So, for example, the project WeLink, the company WeLink, as part of the Aqueduct project, which, again, Joseph Michael is going to talk about a bit later on Thursday. Those are new technologies around, new challenges, and if we want to prepare the industry to cope with the challenges ahead, we need to look at this. It's just a call to action for you. Then quantum processors. Okay, you know about qubit fidelities. It's improving. I mean, if you look at the last results from last year, we have many very interesting results. So 2 qubit gates error, good on the right, bad on the left, log scale for the physical qubits here. And the theoretical useful NISQ zone is over there, there's nobody. And what people do are trying to do stuff here with about 100 to 150 qubits with IBM, or maybe with Google. Now Google is over there. Zhu Shongyi from the Jan Wei Pan's lab, I think, in Hefei is over there as well. So that's where we have the kind of small window with error mitigation that IBM is promoting, and probably Sabrina tomorrow morning is going to talk about that. And then you have a very interesting result from trapped ions over there, the green ones. So getting closer. So my view of that is Napoleon. So it's the battle. So if you're Wellington, it's Waterloo. If you're Napoleon, it's Austerlitz. So maybe those guys will reach the NISQ zone, and probably all they want to do is move up there. So if you're between 99.9 and 99.5 to 99.9 physical fidelities, you can move up if you cross fingers and you hope it scales well with keeping the fidelities as you increase the number of physical qubits in your system. But you remember I was talking about time. Not the time of representation because I'm going to be late, but the computing time. The computing time is linked to the speed of your gates and readout. One big question that Misha was trying to address yesterday is, what are the gates time right now? So that's the first row over there. What would be the kind of optimistic gates? And I would ask the question up to what are the fundamental limits for the gate speed and readout, because I think that's going to be important to improve that for whatever qubit modality there is here. And why is that? I mean, these are the reasons I found out, and probably it's not a good list. It's probably not a complete list. There are many, many reasons why the gates are too slow. And so there's a lot of questions there. And these are theoretical and fundamental questions. It's not just engineering questions. It's the bounds, the role of QSL, What are the energetic vs the speed trade-offs? There are many trade-offs over there. What's the impact on the control? Because the control is costly as well, and so on. I mean, for example, when you have all-to-all connectivity with trapped ions, is it offsetting the cost of the slow gates? This is more a software problem, because you have to optimize your compiler and stuff like that. So there are many, many questions around to look at those problems from both the pure FTQC standpoint and the energetic, I would say, air cover to make that viable. The last layer is going to be quick. I'm going to be on time, maybe. The last layer is the control. And in the electronics, I won't talk about cryogenics. I don't think it's a big problem. There are solutions to improve cryogenics. There were a lot of recent advances that I would like to mention. Last year, Intel, for the first time, developed a new chip called Pendle-3, which was complementing Horse Ridge. And the Pendle-3 is a DMUX chip that works at the lower layer, here at 15 millikelvin. It's connected with a few wires to the microwave encoding, which contains an AWG and ADC, DAX, and everything at the 4K layer, and they're connected. And they're controlling so far just a couple physical qubits for experiments, but it's interesting evolution. They are not the only ones. Many academic labs, including Riken in Japan, are working on that. And it asks a lot of questions, because which are the trade-offs between you simplify the cabling, you put some cryocimos everywhere, but the cryocimos have heat dissipation, so is it worthwhile? So the problem is, en français, on dit pendu fusillé, so it means either you remove the cable, but you put cryocimos and you increase the energy cost, or you keep the cable and you don't know how to address that, or you do some multiplexing, whatever the way. But what Marco Felus and his pals over there found out 2 years ago was that it's better to put all the electronics at room temperature, but you've got the cabling problem, which is not fixed yet. But there were other things interesting. Here, just in Grenoble, for the first time, there was a solution come from Nicolas Roch and Luca Plana, the guys behind Silent Wave. They built a chip that embeds the TUPA, which is the amplifier of the microwave for the readout, and an isolator, which is a two-way circulator. And it's a bulky system in those cryostats. So removing the bulky systems, which are needed for about 8 qubits, because it's multiplex in frequency, it's very interesting that you can simplify potentially the cabling over there. And then there's this SFQ thing. Nobody believes in that. I mean, most of the people I talk about it in France say it will never work. I know the guys who do that in the US. Oleg Mukhanov is Russian, he's behind SICK. Those guys, they must be cared about, because if that works, it's going to solve a lot of problems, at least for solid-state qubits, not the other ones, but it's going to be very important. So again, many questions over there. I've got a laundry list of questions, but how can you make that work? What's your theory behind that? How can you implement readout in a simple manner? Why do you have this complicated system to read out? There are people who try to count the photons out of the superconducting resonator. There may be some ways to simplify the whole stuff. Colab in the US is using a work from Robert McDermott from Wisconsin University that removes all the supply chain of the readout with just one chip at the qubit layer. That's very interesting from the energetic standpoint. Wrap up. You may wonder, I was lying at the beginning. I was talking about the roadmaps. What are the roadmaps? Here are the roadmaps. These are the roadmaps of all the vendors who published a roadmap for FTQC in the last 12 months. So we've got the superconducting guys, including Alice and Bob and Kobe, the locals here. So you have 3 numbers, and not all 3 necessarily. You have number of physical qubits, number of logical qubits, and the number of gates, which is the way to measure the size of your circuit that you can run. Then you've got the atom guys. Then you've got the ions guys. I just put Continuum, which I believe is one of the most serious contender in that space, with the roadmap. And then the photon guys and Candela. One dot is, the red one is the dot for reaching 100 logical qubits. Remember, it's on the left of my chart. The second dot is the green one on the top, is 2,000 logical qubits. What do you see here? 2 things. One is the average there is in 4 years. Can you influence that for the energetic standpoint? I'm not sure. because the academic cycle is not that fast to influence the stuff that's being designed now to be produced in 4 years. So probably what comes out of the QEI is going to influence that, more than that. It's just a guess, a second guess. But it's interesting to see what are the time cycles of academic research compared to time cycles of the industry vendor research, and they have their own research as well. Typically IBM, they have more than 1,000 people. So it's interesting to see how the calendars can match. It's not obvious. I'm asking tough questions here. It's not obvious at all. Another one, the chart that I did, I love to do charts, you see, is how do you compare the estimates of energetic cost of FTQC systems for 4,000 logical qubits. It's an extreme dimension. I prefer to use that because you remember it's in the middle of my chart from DARPA, so it's the middle of the needs for chemical simulations. And the gray ones are the largest HPCs in the world. El Capitan, which is at the Lawrence Livermore lab over there, it's about 40 megawatts in power. And the smaller one is, I don't know, 5 megawatt over there. So there are 500 HPCs that are on the website here, top 50, top 500. And the green ones are potential power drain of future QPUs running 4,000 logical qubits. You may wonder, where do I get these numbers? It's a kind of back-of-the-envelope computing based on public data and sometimes confidential data. This is why I put A, B, C, D here. I don't put the names. But the guys are just in the slide before. You just have to find out which one is which one. It's a good game. And interestingly, if you look at that chart, and it's really based on very raw estimates, there's a 2 orders of magnitude difference between the good and the bad. I don't mean the bad are bad, but that's the reality of the technology. One problem was mentioned just this morning about the cost of the photonic peak. I mean, controlling the photonic peak. We heard that it was too costly. And so as a result, what you see here is most of the planned systems, they seem to be below the threshold of the largest HPCs in the world, which is kind of good news because that may be the threshold. The acceptable threshold may be the largest HPCs in the world. But the best threshold, I would say, is that one. Why is that? Because remember computing time. QPE, many shots, too long computing time. If you want to parallelize your shots across multiple QPUs, it's going to be good to be able to buy several of them, and they don't take too much space. They fit in the data centers. You can have maybe 10, 20, 50, and then you can parallelize, and then you can save time, and you are still below the acceptability threshold from those existing HPCs. By the way, El Capitan cost $600 million. You got to know the price of the systems as well. So that's the price of the largest HPCs in the world. So these are questions. These open questions to understanding the role we play in that community. We want to help that work, and that's going to be important. As a summary, when we created the QEI, I mean, with Alexia, with Robert, with Janine, it was mostly a scientific endeavor. But we are trying to bridge the gap between the science and academic world and the industry world. And this is fundamental. We need that. I am an engineer, but I love science. This is important. Without this, we can't do anything. But we need the other side of the coin, which is engineering. Engineering is mostly to do stuff that you can do potentially, but optimize it economically and so on. Manufacturing, I mean, manufacturing the new lasers, electronics at scale. This is a huge problem. I mean, the guys from Google and Colab, they are on a manufacturing problem. They want to reduce the variability of the qubits on their chip. It's a manufacturing problem. But the other one is system architecture. System architecture is going to be the key point to create those systems. If you look at all the disciplines I went through, I am not specialized enough in each of them, but algorithms design, economics, qubit design, error correction, whatever. You have quantum thermo all over the place, at least on the bottom layers. You have to look at many, many disciplines to create those systems. And integration is going to be a big value in the future to make that work. And economics as well. And that's where we are with the QEI. We are in the middle of that. We are bridging the gap between those two things. That's my message. And this is the laundry list of all the questions I ask. And I may publish some stuff on that later. And that's where we are. What do I have? We have a panel in 2 days. We're going to follow the discussion. We're going to follow the discussion also on the what's acceptable in the breakout we have just after my presentation. And if you want to access my presentation, you've got the slides over there. Use your phone, click. And if you want to look at my book, there's 24 pages on that. Thank you very much.
Well, I'm very happy that this will be on YouTube as well to press pause on each of the slides. So are there any questions on this giant overview?
Thank you very much for this creative and inspired talk. I did appreciate it. I have a question about how mature should be technology or the project in terms of TIL scale in order to be considered for quantum technologies. Like you mentioned.
Wow. You mean from the eye of an investor or?
Yeah. You mentioned in terms of let's say maturity and what's in terms of TRL, like from 1 to 9 scale.
It's a tough one. I will respond to you in a sideways. It's lower than other technologies. I mean, what I've seen, observed, I've been in this world for 7 years now. I've looked at the creation of most of the startups in that space. What I've observed, both from the public funding standpoint and the private funding standpoint, is most of the startups are funded in a lower technology readiness level than other startups in AI or whatever web stuff you have and junk stuff you have in the digital world. That's an observation. And the reason is people believe in all the numbers you get from analyst prediction that is going to create, I don't know, $2 trillion of value in the, I don't know how many years. And the people believe in the dreams. And there's a lot of arguments about this. So when we have all these people believe in the dream, is it wrong or bad? It's both ways. But it's wrong because there's a lot of over-expectations over there. But it's good because it drives the money somewhere and it fuels science. You get funding also indirectly from that phenomenon. And that brings out a big issue for all of us here. It's how do you manage scientific integrity? So how do you fight the high but not too much? I'm myself in a very tough position there because sometimes I am a public advocate on quantum computing, but I want to be honest about what I say. And I know I have to admit that I have a kind of variable geometry here. It's complicated. It's schizophrenic. When you talk with policymakers, talking to investors, that's a complicated thing. I don't know if I answered your question, but we can discuss.
Yeah, but in terms of TRL scale, technology readiness level, it's like 5, 6, 7.
Oh, you want the numbers?
Yeah.
Most of the startups I know are below 5, certainly. Sometimes, I mean, I can give you a couple examples. I mean, I know one team. I love them. They are nice guys. They are based in Chicago right now. The name is HeroQ. I'm going to have a podcast with them soon, published soon. Those guys, they develop spin qubits with electron spins on helium, superfree helium. And when you look at the technology, you look at this and say, oh, that's original. It's never been tested beyond a couple electrons. And how are you going to manage, 2-qubit gates? And they say, oh, we're going to shuttle the electrons over the helium. So, okay. So that's low TRL. But if you look at IBM, it's more than 5, 6, it's up because they are functional stuff, it works. You can test it in NISQ regime, nearly quantum utility regime with VQE, QEM, error mitigation. It's higher up in the food chain. So it depends of the labs of the companies. I see each and every month about one quantum hardware company being created in the world. I was in Slovenia in April. I found one in Cold Adams.
Okay, thank you so much. Yeah, you answered the question.
Yes, sir. Yeah.
Hi, thank you very much, Olivier. It was very interesting. So I actually have an answer for you. So you asked about useful algorithms based on oracles. So I mean, anything that is a verifier of a solution of an equation. So we can use Grover to accelerate, testing potential solutions to equations.
Yeah, but you have to do the math and usually do it really. That's the thing. So.
No, but it's just a verifier, right?
Yeah, okay. Yeah. You have to look at the best solution classically. That's where sometimes you get.
And for the shore, it's not really a business model, right?
There's no business model.
No, but it's not about being a business model, so you don't have to worry about it going to prison because you may be the police and want to use it. The problem with shore,
which is you die.
No, but the problem with shore is shore is becoming useless, right? I mean, we'll abandon RSA.
Yeah, because you have P2C.
Yeah, exactly. So that's okay. Anyway, my question is, why do you equate software to energy? You had this.
Good question.
So you associated energy to software.
I don't equate software to energy. It's my idea with the EFP framework was to say, if you want to optimize the whole energy of a given solution, it's going to be very software related. But if you want to accelerate the speed of your circuit, it's going to be a physics thing, because you accelerate the speed of the physics implementation of your gates or readout. And then if you want to parallelize, it's another problem. Then you want to have many QPUs working together, and it's more an economical problem. So it's simplistic way. Sorry, I'm kind of an analyst sometimes, and so I've got many hats. It's the rationale was that I was trying to put in the three things what was the most rational. So I found out that if you optimize the software, you optimize the total energy cost for the circuit you want to execute. And if you want to optimize either the time or the power, these are the other dimensions I'm looking at. And optimizing the power of the time are more or less independent of the software itself, where the cost is the total energy. Because total energy is proportional to the number of gates and readouts, and this is independent of how you parallelize, and it's independent more or less from the speed of the gates, even though I did show that maybe if you increase the speed, it may increase the energy cost. There are many. But what's true is everything is interdependent. That was what's showing up in Marco Fellow-Saziani paper 2 years ago. I mean, there's so much interdependencies between all figures of merit. And what's good in the QEI and what the QEI wants to spur, I mean, it wants to create as a discipline is understanding the interconnection between all the figures of merit. And it's a very complicated thing, and I think we should all work on that, because not work in isolated places and connect all the dots. And then the optimization may be an NP-complete problem. I don't know, of all of that.
Disconnect the energy from the hardware. That would be my point. But okay, maybe we can discuss.
I put that on the. It was it was my way to explain how to address the computing time problem. There were three ways to do that. Optimize the algorithm, the compiler, which is about the energy of the system. Optimize the gate speed, which is about purely the time. And optimize the parallelization, which is another way to get less time. Yes?
Thank you very much for this presentation. I have a question. Like, if we put ourselves like in 95 and we think about another breakthrough that we have, for example, like semiconductor,
yep.
Would you say that you could do the same presentation with a lot of doubt, or would we have been more sure that this technology will work and that we will be here with working computer and HPC center?
Yeah, it's a very good question I have frequently. Are all the potential complexities of building a quantum computer or the doubts we may have about it different from the doubts maybe people had 30 years ago, 20 years ago? I was there. I mean, I'm older than most of you here. So I was there. I saw those revolutions, and those questions were not raised. One of the reasons, there are two reasons which I don't mention. One of the reasons is Moore's law was in place. I mean, Moore's law stopped more or less in 2006, at least because of the leakage that was described by Misha again, I think, yesterday. But before that, every year you had a faster clock rates, you got more transistors, more features, and blah, blah, blah. But the big difference, the huge difference between the advent of quantum computing and what we had before is that quantum computing is competing with legacy classical systems which themselves are improving. I mean, one example is AlphaFold. AlphaFold, the famous protein folding software from DeepMind in the UK, it's from Google. They released recently the AlphaFold 3. It's going beyond protein folding. It does way more stuff. They are partnering with EMBL, which is, I don't know, based in Luxembourg, I think. So they have a huge database of all proteins around. They are doing stuff that 10 years ago we believed should be done with the quantum computer. And now they do it classically with a bunch of NVIDIA DGX servers. So I would say I've never seen such a competition of existing systems. The only historical thing I have is the Lisp machines from the late 80s, early 90s. Back then, there were a couple of startups, just 5 of them, mostly in the US. They all wanted to create Lisp machine to do AI. So symbolic AI to do expert systems, stuff like that. They were designing custom processor for that. They got killed. And the reason why they got killed was that Intel, which was the leading, not anymore, but it was the leading chip vendor back then, they were improving their system, which are generic CPU systems, faster than whoever would do that on a dedicated system on Lisp. So that's linked to one of my words in my slide at the beginning. Intel was versatile, generic, it was a platform. Everything could run on it, and all the others were dead. Like workstations, Unix workstations with Sun Spark processors, dead. Mini computer, dead. Linux killed everything. It became Intel-based processors and PC kind of servers. So the genericity completely changed the market. Even the TV business, they went out of business. All the specific hardware they had, it became servers from Dell EMC. Same in Huawei, vs Alcatel, and Nokia and Ericsson. Everything became EMC, Dell, and HP servers. It became a software business. So there are interesting parallels to look at in the history of computing, definitively. Yeah.